Now, just before I start the next topic, on Wednesdays, I don't think it's on your timetable, but I think on Wednesday at 1 o'clock, like over there, Wednesday at 1 o'clock, there's an extra math class. So if you can see Wednesday, Wednesday at 1 o'clock, I think this is the time. I don't know, because, because there's no more grab this then. And there's an extra math class. In this class, you don't have to go. It's just an extra class for more math contact. I won't do anything new in the class. I'll just do, whatever problems people are having. Maybe I'll do an exam question. Maybe I'll do some revision. Whatever people need, okay? I think you had a class like this last semester with Joan or Roland or something, or not? Oh, no, you haven't? Okay. Yeah, who was that with?
With Joan.
It was with Joan. Yeah. Yeah, but you're free at 2 o'clock. Hey, you're free at 2 o'clock on a Wednesday.
Your class is during our lunch.
Dude, take your lunch at 2 o'clock. It won't kill you. You know what I'm saying?
We have 2 o'clock. We have 2 hours.
Yeah.
Okay, then
Don't worry, okay? You'll get your sandwich, alright? Yeah, that's fine. No, hang on.
Then I come for 2 hours.
But I'm only going to be there for 1 hour, so you can stay there for 2 hours if you want. The room will be free. So anyway, 1 o'clock on a Wednesday. I think it's A401. Maybe I'll bring the projector, maybe not, I don't know. I'll see what people want, okay? It's only if you feel like you want some extra time. Okay, so we'll continue with the next lesson now. Page 70, please. There we go. Come on. Oh, there we go. Okay. Ooh, colors. We're back. Right. I'm just waiting. There we go. Okay. So before, actually a little bit of vocabulary before we start. Rational function. So if you had something like a linear or a quadratic or something like even a quadratic and a quadratic, or if you had like a cubic and a linear, these are all examples of rational functions. What I mean by rational is the top is something like x power n plus blah blah blah, and the bottom is x power m plus blah blah blah. So that's what I mean by a rational function. You know, something like a quadratic and a quadratic, or a linear and a cubic. These are rational functions. And we're going to look at some special types. So for this lesson there are four types of rational functions we'll learn how to integrate. And I'll show you how to integrate them. And again, we use a substitution. So here's our first example. There we go. Minus 8x plus 6 over minus 4x squared plus 6x plus 5. Come on, scroll down, there we go. Dx. So, what do we have on the top? What type? Linear, and the bottom? A quadratic. But maybe somebody can see there's a special relationship between the top and bottom, that there's some way they're connected. How are they connected here? Can anyone spot their connection? You know what? You're right. But not what I want. Albert! In English, please. Well, not quite.
They can multiply by x.
No, we're not seeing it. The top is the derivative of the bottom. That's okay. Now, when you have this situation, when the top is a derivative of the bottom, or the top is a multiple of the derivative of the bottom. So, for example, if there was a 2 here, it's still fine. What you do is you let u equal to the bottom. Whoops. So du dx equals minus 8x plus 6. So du over minus 8x plus 6 equals dx. So we can go back here and change this into minus 8x plus 6 over u du over minus 8x plus 6. Cancel, cancel, and you're left with 1 over u du, which equals log u, which equals log minus 4x squared plus 6x plus 5 plus c.
It's not like you can do that, like you have to add something.
Sometimes it could be like this.
Like maybe to get some functions outside and you add it together.
Usually, yes. But you might get lucky. Okay, can I continue? Yes? So this is a linear over a quadratic. Will this always work? No, it won't always work. There needs to be this special relationship between the top and the bottom. Okay. Next example is when we have a linear over a linear. And here our method always works. We let u equal to 2x minus 9. Du dx equals 2 du over 2 equals dx. So I can go back here with this one and with this one, and I get 6x minus 7 over u du over 2. So I get a half 6x minus 7 over u du. Same problem as the last lesson, but we can say u plus 9 over 2 equals x from up here. So this would be a half 6 u plus 9 over 2 minus 7 over u du. Now, what you could do here is, if you want to make this easier, you can multiply the top and the bottom by 2. So here you get a half 6u plus 9 minus 14 over 2u du. And again, this 2 can be taken out, or actually, better, this 2 can be divided. 2 into 2 once, 2 into 6 3 times, 2 into 14 7 times. So you're left with a half 3u plus 27 minus 7 over u du. So now we're left with a half 3u plus 20 over u du, which is a half 3u over u plus 20 over u du. Yeah? So this is a half integrate 3 plus 20 over u du, which will be a half 3u plus 20 log u, which will be 3 over 2u. What did I say u was? 2x minus 9, wasn't it? Plus 20 over 2, which is 10 log 2x minus 9 plus c. That's the answer. Quite long to do. Much longer than the last one. Yeah. Yes, continue. Okay. Next. So before we do the next two, I have to prove a small result. And in fact, I think you did this proof last week actually. Did we do 12F? I think we did that in the class. On page 66. Page 66. On page 66, I asked you to use implicit derivatives to calculate the derivative of tan inverse f. And we had to draw a triangle. Can you find that in your notes? Yeah? So, from your notes, what is the derivative here? Yeah. It's 1 over something. Correct. This is from page 66, 12F, which we did in class. So I won't go through it again, but the result is useful because on the next line, if we integrate, we can say tan inverse x equals the integration of 1 over 1 plus x squared dx. So if you remember, if I start here and go here, this direction is derivative, like here, this direction is derivative. So going backwards is antiderivative integration. So if the derivative of tan inverse x is 1 over 1 plus x squared, therefore the antiderivative of 1 over 1 plus x squared is tan inverse. So this result is what we need for the next two examples, plus c of course. This is from last week. Okay, did you write that box down? This is important. Okay.
Why you have C inside?
No, it's not inside. Oh yeah, why do I have that? See, well, it's fine. I should have it on the other side, shouldn't I? Plus C here. Oh, it looks ugly. Forget about it. You know the C goes in it. Yeah. In fact, Malik, it wasn't wrong to have the C on the other side. You can put it on either side. It's fine. Okay, so let's have a look at an example now. So I want to integrate this. Yes, continue. So what you notice is that this is a little bit like this formula, but it's still a bit different. So there's a trick here to simplifying. What you do is you say let u equal the square root of 4x squared over 1. You let u equal the square root of this piece over this piece. Now, you'll see why that's useful in a moment. That means u equals 2x over 1. So that means u equals 2x. So what does du dx equal? Well, that's 2. So dx is du over 2. Also, what does u squared equal? What's u squared? 4x squared. So these two results are very useful. Because here I can change this into 16 over u squared plus 1 du over 2. Because this piece here replaces this piece. And the dx is replaced by du over 2. So this becomes this becomes 8 over u squared plus 1 du, which is 8, 1 over u squared plus 1 du. Now what do I have here? Well, this is my new formula. What does that equal? Tan inverse u plus c. So finally I get 8 tan inverse 2x plus c. So the trick here is this. Let's get a nice blue. The trick is this part here. You let u equal the square root of the first over the second. This simplifies it for you. You would never have guessed that. So this is one you would need to remember. Okay. Can I do another one? Scroll down. Did you say wait a minute? Right, try this now. Let's have a look at this. 16 over 4x squared minus 8x plus 8 dx. Well, the first thing you can do at least is divide everything by 4. And I suppose you could take the 4 out if you want. So, what's the problem here? Can we use our same trick as before? No, why not? There's 3 terms in the denominator, and our trick was for 2 terms. Any ideas on how we could fix that?
Can we simplify the pattern?
Yeah, but how to simplify? Not this. Good try though. Something else to simplify it. You want only 2 in the bottom. Factorizing is not too bad, but the problem with those 2 is they're multiplied and we'd like to add it together. Well, what's this called? What's this called? Ah, yeah. Complete the square. We'll make 2 in the bottom. So you can change this into 4 over x plus 1, no, x minus 1 squared plus 1 dx. Now we can use our trick. Let u equal the square root of the first over the second. So u will equal x minus 1 over 1. So that means u will equal x minus 1. So that means du dx equals 1. So that means du equals dx, which is nice. And also we can say that u squared equals x minus 1 squared.
Is the top one the formula or what?
This here, is it?
Yeah.
Is x minus 1 squared. Yes. It was, whoops. It was this piece divided by this piece. This is the trick for these, yeah. Okay. So this will equal 4 over u squared plus 1 du, which will equal 1 over u squared plus 1 du, which will equal 4 tan inverse u with the plus c. So this is 4 tan inverse x minus 1 plus c. Now, you might think you can use this in a lot of situations, but you can't. There's a big problem if this here is a minus, for example. Why is this a big problem if this is a minus 1 instead? Why is that a problem?
Because when you can't get the first one when you square it.
No, not a problem. Come on guys, tell me, why if this was a minus 1 would that be a big problem here? No? What? Yes? Yeah, here. If this is minus 1 here, then you end up that you have to stop because you can't actually do this. There's no root of a minus. So for these problems you should get a plus here. Can you do it if it is a minus? Yes you can, but not this way. That's a different lesson. Yeah, so this is a big topic now. So already we've seen 4 different types of fractions, and there's still, I think, maybe 4 more to do. Okay, so let's see, I think you'll try these for a few minutes. Oh, now just before you do them, just to say in the exam, it would usually, come on Marcelo, usually in the exam they give you Junway, go back to where you were. I didn't like the way you leaned back there and suddenly relaxed. It didn't feel good. In the exam, usually they give you some limits. You know, they put some numbers here. That's no big deal. It just means at the very end here, you have to put in the limits. So none of my questions has limits in it. But just so you know, in the exam, they usually have the limits. And also in the exam, when they do have the limits, they often want the answer exactly. So for example, here, if you had like tan inverse 1, on your calculator that's pi over 4, and they want you to keep it like this. They don't want it simplified. Usually in the exam. Make sure you read the question carefully to see if you see this word. If you see the word exact in it, they want the answer like that. If you don't see it, then they don't care. You could write the answer like whatever. 0.9. Yeah.
When you have the x inside and the x outside, how do you substitute?
Inside and outside? What do you mean?
Not this example, the previous example.
Inside and outside?
Like 4x, then 2x.
Give me your example. 4x, tan, whatever, tan inverse x, yeah?
Yeah.
It doesn't matter, the x's get replaced at the same time, you know. You put in the first number, and then you put in the second number. Yeah?
But is it in radian or?
Oh yeah, good question. What do you think?
Radian?
Yes, these are always in radians. It is. I saw something new today which I better tell you about in the exam. So this is X. No, sorry, let's try this again. What angle is this? Marcelo? No, sorry, apologies. Victor and Remo. Please listen, this is important for the exam. Exam is important, right? Yeah, well, it should be. What angle is this? 60 degrees. And this one here would be 60 radians. Now, has anybody ever seen this before? No. I have never seen this in my life before. Joan, the other maths teacher, she has never seen this in her life before. And Roland, the other maths teacher, he has never seen this in his life before. And nobody here has ever seen this in their life before. But the person who wrote the maths exam used this symbol in the exam last week. And we're all like, what the heck is this? And you may be surprised to know, does anyone want to guess what it is? 60, the angle is 60 Celsius now. It's radians. Yeah. Yeah, I know. So if you see that in a diagram, it actually means radians.
Did you tell the
No, because it said it in the question at least. So the question then also said, for example, A equals 60 radians. So it was okay. But I've never seen that in my life before. And I checked it on Wikipedia and apparently it's a real thing. So yeah. No, that's true. Maybe the person who wrote the maths exam uploaded that entry over the weekend. I don't know. Yeah. Okay, try these for a few minutes. Let me close this.